Hello everybody and welcome to Simple Harmonic Motion Lesson 2. Now in the last lesson we looked at the two key conditions for SHM which are there on the screen where displacement is proportional to acceleration, but displacement and acceleration are always in the opposite direction to each other. We also defined amplitude as the maximum displacement from the equilibrium position, and we defined what one complete oscillation was, and then moved on to look at time period and frequency in simple harmonic motion. We also came up with the equation to link acceleration and displacement as being A is proportional to minus x. Now, one of the aims for this lesson is to look at that equation, A being proportional to minus x, see mainly if we can prove it in this lesson, and also hopefully we can get the constant of proportionality out of that as well. Now, also to remind you from last lesson, here's just a screenshot, or at least part of one of the slides that we had last lesson, where we were looking at where x is maximum, where x is zero, same for velocity and acceleration. Now, what we're going to do for the purposes of today is we're going to imagine taking a pendulum system, and we're going to start it at positive x max. So this will be our first point when we come to graphing this data in a minute. So we'll say that at that point t is equal to 0. In other words, we're going to displace that pendulum to the right to positive x max, or to the positive amplitude, and when we let go and therefore set it into SHM, we will start the time, so therefore time is equal to 0 at that point. Now, as we said before, by definition, when it comes back to that point again, we will have completed one complete oscillation, and therefore the time will be capital T for time period when it gets back to that point. But there are a couple of other points which we're going to have to take into account along the way. From positive x max, it will then move to the equilibrium position, so that will be our second point. From there it will then move to the negative amplitude position, that will be our third point. It will then go back to equilibrium, point number 4, before it comes back to positive x max again after one complete oscillation, so that's 0.5. So we can see that what we're doing is we're splitting one complete oscillation down into 4 different sections, into 4 different quarters. So because we're splitting it into 4, we're treating each portion as quarter of an oscillation. So at this point, at point 2, when we've gone back to the equilibrium position, at that point we're a quarter of a time period will have elapsed, t over 4. At this point, half a time period will have elapsed, t over 2, and then back to this point again, 3/4 of a time period will have elapsed. Now, what we'll do is in a moment we're going to jump on to trying to graph this and splitting it down into those bits. If when I'm graphing this you need to sort of jump back and forth between what's currently on the screen at the moment and what's about to be on the screen, then so be it. What I'll be doing is I'll just be going straight into the graphs. Okay, so let's get on with graphing this then. Firstly, let's do the displacement against time graph, and what we'll do is we'll do this for 2 complete oscillations. So we'll take that point there as t, one complete oscillation, and that point there as 2t for 2 complete oscillations. Now obviously what we're going to end up doing on the next graph down, we'll have velocity against time again for 2 complete oscillations, and then thirdly we'll have acceleration against time yet again for 2 complete oscillations. So hopefully you can see where I'm going with these graphs already. I want to get 3 graphs, one above the other, so that we can see and we can compare what's going on between the 3 graphs that we're about to draw. So coming back to displacement then, if we mark on a couple of points where we have positive amplitude and down here we have negative negative amplitude. And let's just remind ourselves about how we said this motion was going to go. We said we were going to start at t equals 0 at positive amplitude there, and that after one complete oscillation we're going to be back to that positive amplitude, and therefore obviously again at 2 complete oscillations we'll be back there again. We also said that at a quarter of a time period and 3/4 of a time period we're going to be at the equilibrium position, and the same will go for 1 1/4, 5/4 and 7/4. Finally then, we said that at half of a time period we were going to be at the negative amplitude position, and the same will go for 1.5 time periods or 3/2. Now on the screen now and on that graph you can see that we've plotted the points that we thought about in the last slide. Now looking at that, there are only really a couple of shapes that this graph is going to be, and I hope that it's going to be obvious, and we'll show you why in a moment anyway, but I hope it's going to be obvious that it's not going to be a sawtooth graph where we have sort of nice defined peaks. It is going to be a sinusoidal graph, okay, which if you're good at maths you will also be able to tell me that it looks like a cos graph. Moving on to velocity then, so once again we can put on positive V max, and we can put on negative V max onto our graph straight away. On the previous slide then we said that, well, when A is at positive amplitude, velocity will be 0, and in fact every time we hit one of the amplitude positions, whether it be positive or negative, going back to that last slide again, velocity will always be 0. So immediately whenever we get an extreme point, an amplitude point, we can mark on our graph that velocity is going to be 0. So those points there are where V is equal to 0. Now of course we know we're going to get some kind of sinusoidal graph on this. It just really now is a matter of determining in which direction and what kind of shape it's going to look like. Now of course in our thinking we displaced to positive amplitude, which of course is to the right, and that's where we started. So in other words, the pendulum would be in that position there. Now as soon as we let it go into simple harmonic motion, it's going to move in that direction. It's going to move to the left. So therefore, remembering that right is positive and left is negative, the velocity will become negative at first. What we're going to end up with then is what's going to look like a sine graph, but it will actually end up as a negative sine graph. In other words, it will look like this. Finally then, for acceleration, once again we can have positive A max and we can have negative A max on our graph. Now there's a couple of different ways that we can look at this. Firstly, we can note that at this positive amplitude position velocity is 0 and then it moves to the left, and therefore acceleration at that point must be acting to the left as well, and therefore acceleration will start off being negative. We also remember our two key conditions for SHM as well, which say that A and X are proportional to each other but in the opposite direction, and therefore when we apply both of those ideas to this graph we can see that while the displacement graph was a positive cos curve, this will end up as a negative cos curve. So there are all the points, and the curve will look like this. Sorry that that's not perfect, not bad, but obviously just on the graphics pad that's not the easiest thing, but hopefully you can all see, and when you obviously do your notes you can get a nice smoother curve for a cos graph out of that. So at the moment then we've got 3 graphs, but the next stage is going to be to try and put an equation on these graphs. Now let me just make over here a little bit of space. Okay, let's do displacement first. Now what I'm going to do, I'm just going to throw the equation at you first. I'm going to say that x is equal to a cos of omega t. Now that is the equation to describe the graph for displacement. Now straight away we can see that we've got an omega has appeared in there, and we remember from the circular motion topic that omega is 2 pi over t, or 2 pi times the frequency. Now what I'm going to do, I'm just going to flip over to a new slide to show you why that's the case, and hopefully just to prove to you that that is the equation to give that blue line that we've got on the graph there. And then we'll come back to this slide and then I'll work through and we'll show you what the equation for V and for A are. So let's just satisfy ourselves that that is the correct equation. So I've brought those over from the last slide, and just remember that omega we're going to use for these purposes 2 pi over t. Now what I want to do is I want to just plug some numbers in really and see what happens. So firstly let's see what happens when t is equal to 0. Well, when t is equal to 0 we have x is equal to a multiplied by cos of, well, it's omega multiplied by 0. So obviously omega multiplied by 0 is equal to 0, so we end up with here cos of 0, and cos of 0 is equal to 1, and therefore, well, if this bit here is equal to 1, then all we're left with is x is equal to a. Well, that's exactly what we were expecting on the graph. Let's have a look at t is equal to a quarter of a time period. So when we do that, x is equal to a cos of omega, now we will put in as 2 pi over t multiplied by t, which now is capital T time period over 4. Now inside that bracket we can see the capital T's cancel out, and the 2 will cancel out with a bit of the 4, and what we end up with here is cos of pi over 2. Now of course we're working in radians. Cos of pi over 2 is the same as saying cos of 90 degrees, which of course is 0. What we end up with then is that this bit here is equal to 0, and therefore the displacement is also equal to 0. Coming back to the graph, once again, that's exactly what we expected. The next stage, t is equal to t over 2, so half of a time period. So again, x is equal to a cos of 2 pi over t multiplied by t over 2. Once again we can see we have cancellations, the time periods cancel out and the 2's cancel out, and what we're left with is cos of pi. Now again we're working in radians, so cos of pi, if you're working in degrees you'll understand it as cos of 180, which is minus 1. You can now see that we're going to be left with x is equal to negative a. Well, come back to the graph. After half a time period, we're at the negative amplitude position. If we just do one more, I won't bother doing 3/4 t because it's going to end up as the same as t over 4. Let's just do it after one complete oscillation, so after one time period. So x is equal to a cos of omega 2 pi over t multiplied by t one time period. Once again, the t's cancel out, and what we're left with is cos of 2 pi. Now, of course, cos of 2 pi, if you, like I said, still working in degrees, cos of 2 pi is cos of 360 degrees, but cos of 360, cos of 2 pi is exactly the same as cos of 0, which is therefore equal to 1. So we end up back with exactly the same results that we had up here. X is equal to A. And on the graph, X is equal to A. So hopefully you can now see that we've tested it with some points on the graph. I'm not going to go on because it is going to hold up for any number that we plug into that for fractions of a time period. So hopefully now I've managed to convince you that X is equal to A cos omega t is the equation to describe the graph of displacement against time. So back to these three graphs then. So we've got our equation for displacement. We now, at least algebraically, need to get an equation for velocity. And of course, if we're going to calculate, we're going to derive velocity, then we're going to take the rate of change of displacement. From a maths point of view, therefore, we're going to take the equation x is equal to a cos omega t, and we're going to differentiate that with respect to time. Let's work through that then. So v will be, well, firstly, the amplitude is a constant, and therefore when we differentiate, that's left alone. When we differentiate cos, in maths we know we get minus sine of omega t, and then from maths, once we've differentiated, we also need to differentiate what is inside the sine as well, and therefore we also need to differentiate omega t with respect to t. That will therefore give us an extra factor of omega to multiply by, and a final equation for velocity therefore becomes negative a omega sine of omega t. Now hopefully a lot of that shouldn't surprise you, because when we look at the graph on the left hand side, we can see that the shape of that graph is a negative sine curve, and that's exactly what the theory and this derivation has shown us so far. The next stage then is to go from velocity to acceleration, and once again we're going to differentiate with respect to time. So a is equal to, well, the negative a and omega, all of those are constants, so when we differentiate, that doesn't make nothing happens to those, they just stay where they are. What we're left with then is the sine of omega t bit, and when we differentiate sine we get cos, so minus a omega cos of omega t, but once again we need to differentiate what's inside the sine, and therefore we're multiplying by another factor of omega. Now because we've got an omega there and we've got already an omega there, what we end up with is a is equal to minus a omega squared cos of omega t. Just to create a little bit more space then, I've brought those three equations forward onto a new slide, and actually we're almost there. We've almost now got the final equation that we're looking for. Now I want you to have a look at the acceleration equation, and in that equation you'll notice that we've got amplitude there and we've also got cos of omega t. If we go back up to the original displacement equation, we can see that displacement is a cos omega t. So in the acceleration equation we can now get rid of these two bits, the a and the cos of omega t, and we can substitute back in the displacement that we originally came up with from the equation point of view. And what we're therefore left with is A is equal to, well, we've got a minus, we've got an omega squared, and now we can put the x as displacement in there. Now what we've managed to do firstly is we've managed to derive what's known as the general equation for SHM. Now as usual, this being a general equation, this applies to any simple harmonic motion system. Obviously we can then use that and do some derivation to determine a more specific equation for specific systems, and that's going to be the subject of at least the next couple of lessons and the next couple of videos. But as I said, any SHM system will obey that equation. Now what we've also managed to do, again if you remember back to the last video, we said that A is proportional to minus x. What we've managed to do is prove that proportionality, prove that A is proportional to minus x, but we've also managed to replace the proportional sign with the equal sign and the constant of proportionality. Now, of course, what that implies is that omega squared is a constant. And because omega squared is a constant, when we substitute in 2 pi over t, obviously remembering to square all that, is a constant. When we look at all of this, well, 2 and pi are just numbers, and the only thing in there that could possibly vary is the time period, and therefore we can say that the time period is also a constant. So that's it for this video. Again, there won't be a question for you to do in this one. Over the next couple of videos though, as we start to delve more into the more specifics rather than dealing with SHM in extremely general terms, then we'll start to introduce some questions into the videos as well. So just to summarise this video then, the main crux of the video was to derive the general equation for SHM, which is A is equal to minus omega squared multiplied by x. And in this equation, omega squared is considered to be a constant, which implies that the time period of an SHM system is also a constant. In the video we also did the equations of motion, so x is equal to a cos of omega t, v is minus a omega, sorry not cos, it's sine, and finally acceleration is minus a omega squared cos of omega t. So as I said, that's it for this lesson. Any issues, any questions, please get in contact with me and I'll see you next time.